Okay. The adjoint of a matrix is a transpose of the matrix of cofactors. And let's see, I always worry that Zoom has died when I don't see myself there. Okay, well, remember the cofactors of the matrix. Let's just do an example. Okay, let's say the matrix is 1, 2, 3, -1. Actually, that's a pretty sorry matrix. Well, I'm going to do it anyhow. Okay, the cofactors C11 is what you get, if you recall, by eliminating the first row and the first column, taking the determinant of what's left, which is just -1, and of course multiplying that by 1. So it's 1 times -1, which equals -1. C12, you go to first row, second column, and you have the number 2. Now it's, to be careful, it's -1 to the 1 plus 2. -1 to the sum of these two numbers, the sum of your number of the row and column, and it's then times the number here, and then what you get if you eliminate its column and row, which is 3. So there's your cofactor 1, 2. Now I don't want to use up space up there, so I'll do cofactor 2, 1 is the row 2, column 1 number, which is 3, times -1 to the 2 plus 1. Multiply that by 3 times the matrix you get, and of course it's just a number in this case, when you eliminate that row and column, which is 2, which is going to be -6, and then C22 is -1 to the 2 plus 2 times the 2, 2 number times the matrix you get when you eliminate the row and column of this one, which leaves you with the 1, and that equals -1. I hope I've calculated all those correctly. Okay, so the adjoint is transpose of C11, C12, C21, C22, which is the transpose of -1, -3, -6, -1, which equals -1, -6, -3, -1. If you then divide the adjoint by the determinant of the original matrix, you should get the inverse of the matrix. Now, you must have done something wrong here because it's not going to happen. Actually, maybe it will. Yeah, that's actually going to, no, that's not. So I must have miscalculated something. Either that or I had the pattern wrong. But that -6 is bothersome. So get the pattern right, but the idea is simple enough, and do the calculations correctly. Okay, the determinant of your original matrix, 1, 2, 3, -1, is -1 minus 6, which is -7. Okay, so the inverse of this matrix should be 1 over -7 times the matrix -1, -6, -3, -1. It isn't, because if I multiply this matrix by this matrix, I should get 0 when I multiply the first row by the second, and I don't. And that 1/7 doesn't make any difference. I should get 0 when I multiply the second row by the first, and I do. So I think something is right here, but one of these, I don't know what I might have done. But I think the problem is the 6, which is your C21. Aha. No, never mind. No, that's right. Okay, I'm not going to worry about the calculation, but that's a little bit about the adjoint. And the fact that if you do this thing with the cofactors, do its transpose, and then divide by the determinant of the original matrix, you get the inverse of the original matrix. That's kind of neat. Other things is the adjoint is really kind of a powerful tool to use in proving certain things that turn out to be pretty important. Okay. So I screwed that up somehow. And I apologize for that, but it's a fairly simple idea. Now, an even simpler thing, and I mean, I learned this in Algebra 2, maybe even Algebra 1, when I was just, 3 or 4 years old. Well, that's a luck, older than most people are when they take those courses now, because we used to teach them later, and people used to learn them a lot better too. Since we're teaching them to younger and younger people with less and less background, maybe it makes sense that we're not teaching it, but it seems so simple. And what I'm talking about is Cramer's rule. So, if I have a system of equations, and let's take a system of 3 equations, 3x plus 2y minus z equals 8, negative 2x plus y plus 2z equals 3, and x minus y plus z equals 5, and I hope none of those is a multiple of any of the others, but if it is, we'll discover it. Okay? First of all, you have matrix 3, 2, -1, -2, y, 2, x, 1, -1, 1. Okay? That's going to be an important matrix. I'm going to call that D, because everything we do is going to be a determinant divided by a determinant. And it shouldn't be a y there, it should be a 1. And the denominator determinant is going to be this, okay? Then, we're going to do, now there's a notation for this, and I haven't thought of the notation, I didn't bother reading the book on this. to check the notation, and I probably should have. So I'm just going to call it C for Cramer sub x. To get the C sub x matrix, you replace all the coefficients of x with the numbers over here. So all the coefficients of x are here, and the numbers over there are 8, 5, 8, 3, 5, and then the D matrix continues, or you just continue as the D matrix does. CY, you take this matrix and you replace the Y column with these numbers. Just try to be careful. I'm not actually going to compute these things. And then CZ, you replace the column of coefficients of Z with these numbers. The first two columns are as they are, and then your last column is the Z column, and that'll have the 8, 3, 5. Okay? Well, once you do this, your solution is x equals the determinant of your CX matrix over the determinant of your denominator matrix. Again, the denominator matrix having all the coefficients of the x, y's, and z's. Y is a determinant of CY over the determinant of D. And Z is the determinant of CZ over the determinant of Z. Now you easily put the numbers in, calculate the determinants. Probably seems like a lot of effort to go to when you can just invert the matrix and so forth, but it's also kind of an important application. And you know, when I learned this at a very tender age, I did. We only did it for 2 by 2 matrices. Okay. But it works for any dimension. Not the most efficient way to solve a system, but again, it's of interest. And it's probably not taught that much anymore because it's not the most efficient way. Okay. Other applications, let's see. Yeah. Area of a triangle. Okay, so we have a triangle with point x1, y1, point x2, y2, point x3, y3. Now, if we have the x-axis down here, and these of course don't all have to be above or all below the x-axis, but here's our triangle. Now we can form 3 trapezoids, and you might wonder why in the world we bother. It's because we get something pretty easy, pretty neat, and also something that extends to higher dimensions. Okay, so we have a trapezoid here. Now I do trapezoids because it's really easy to write the area of a trapezoid. I'll do that in a minute. Then I have another trapezoid here. And another trapezoid here. So I've got a trapezoid for x1, y1, and x2, y2, and a trapezoid for x2, y2, and x3, y3, in addition to this bigger trapezoid down here for x1, y1, and x1, y3. The total area of the triangle is the area of the trapezoid. Well, it's the area of this figure, which isn't a trapezoid, minus the area below. Okay? So it's all the area below the triangle minus the area below the lowest side. The area below the lowest side is the area of this trapezoid. The total area is the area of this trapezoid plus this trapezoid. Okay, I've got two trapezoids that make up the total area. So, the areas of the trapezoids are, okay, let's take the one for x1, y1, and x2, y2. The width of the trapezoid is x2 minus x1. That's what I'll call the width. And the average height, as we read it this way, is just the average of y1 and y2. Halfway between y1 and y2, but that's what you get when you average y1 and y2. It's the average of y1 and y2 because this is a straight line. So if you go halfway along that straight line, the y-coordinate is y1 plus y2 divided by 2. If you cut the trapezoid like this, you get a rectangle that's equal to the area of the trapezoid because the area of what got cut out is equal to the area of what you add. And you want to look at that and understand that. It's kind of important. Okay, there's your average height. Okay, well that's an upper trapezoid. The other upper, kind of fun to say that, other upper, okay, is x3 minus x2, because that's the width of this trapezoid, x3 minus x2, times y2 plus y3 over 2, because you're averaging your y2 height and your y3 height. And then the lower, we can see, is x3 minus x1 times y3 plus y1 over 2. Okay? Well, the triangle area is the sum of the two uppers, because the two uppers make up this house-shaped thing here. And then you subtract off the lower, and you've got the area of the triangle. This equals the determinant of the matrix, x1, y1, 1, x2, y2, 1, x3, y3, 1. If you expand along the first column, you see you're going to get x2, y3 minus y2, x3. Okay? And if you look here, you get an x2, y3 and an x3, y2. And then you get a couple of other things that when you expand all these things and add them up, some stuff cancels out and you end up with this determinant, which is, if you want to write it out, Okay, 1 times the determinant of this, 1 times the determinant of this, it'll be minus x1, y1, minus x2, x1, y2, minus x2, y1, and it's y3 and x3. And then it's plus 1 times the determinant of this, which is x1, y2, minus x2, y1. Well, there's your determinant, and this is identical to what you get here. Okay? Now, what happens if this determinant happens to be 0? Now, I don't want to belabor this too much. If the determinant is 0, the area of the triangle is 0. Now, if this is a normal class, I'd drag it out of you what that means. But what that means then is, how could the area of the triangle be 0? Well, if you have 3 points that almost lie on a straight line, but not quite, you get a really small area because you got a really small altitude. As this point approaches the line, the area approaches 0. Well, from that you can think, and it's a fairly intuitive idea, I think, that means your 3 points are on a straight line. Okay. We can extend this to 3 dimensions. If you have 4 points in 3 dimensions, you get a tetrahedron. Now we're running short on time, and normally I wouldn't mind going a little over on time, but I've got a class in the last day of taking a test, and I'm going to leave what I'm doing here and enter a situation that nobody wants to enter, but I do want to enter because I want to see how they do and I want to help them out. Okay, so, but we're going to go over a little bit because we lost time when my modem crashed, so we're going to go over about 15 minutes. If you've got to leave, you may, because all this is being recorded.